as we saw last day, our try with the online live class was not successful. So I'm trying this method instead. I'll be writing or rather typing on a Word document with my voiceover alongside. Let's see how does this work. So today we'll be doing Cantor's nested interval theorem. This is a very important theorem from the point of view of real analysis. The system of decimal representation of real numbers, or rather any representation like binary, octal, hexadecimal of any sort, stands entirely on this. If you remember, at the beginning of the course, among many questions posed which were to be solved during this course, this was one of them. We have already seen that a few real numbers have more than one decimal representation. Like 1 is same as 0.9 recurring. Yeah. So there can be something fishy. Two different decimal representations is giving you the same number. So maybe we need to introspect the consistency of this representation system, decimal representation system. So to do that, so there can be something fishy. So now when we write this number, let's say square root of 2 is equals to 1.414213562373 and dot dot dot, then what does this dot 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 mean at the last? This means that if we continue this way, we will get a number. We'll get a number which is supposed to be root 2. But what is the guarantee that we will get a number and we'll get only one number over there? Cantor's theorem answers this question. So Cantor's theorem actually justifies the consistency of decimal representation system. So let's see the statement of the theorem first before we go into any other further discussion. So the theorem says this way: if ANBN is what did I do? This here it will be this way, yeah. If this is a sequence of or sorry, I say nested sequence of closed and bounded intervals, then and infimum of the length bn minus an is going to 0 is equal to 0, then okay, there is something going on. Okay, then the intersection of everything, you need to bear with this problems once for some time. In slash n, yeah, okay. All these a and bn's, an comma bn, this is precisely a singleton set. So this one is a singleton set. So it says if a and bn is a nested sequence of closed and bounded intervals, then and the length of those subintervals are going to 0, then this is the intersection. All of them will contain precisely one point. So let's see what does this mean. So here I have got a diagram for you. So here you see what do we mean by nested sequence. So nested sequence means this thing. that the first interval A1 B1 is the biggest and it contains everything else. So you see here you have got A1 B1. This contains the entire everything. Everything is happening inside A1 B1. What is there inside A1 B1? We have got superset of A2 B2. So A2 B2 is somewhere inside A1 B1. So here is your A2, here is your B2. So that is inside A1 B1. This is again inside A3 B3 and so on. So A3 B3 over here, A3 B3, this is inside A2 B2, A2 B2 is inside A1 B1 and so on. So A1 B1 is the largest, then it contains A2 B2, A2 B2 contains A3 B3 and so on. So the A4 B4 is contained inside A3 B3 and so on. So in this way I'll write superset of AN BN in that sense. As this continues, let me put some dots here. This is a superset again of AN BN, AN comma BN, and this continues, doesn't stop here. So dots. So this is what we mean by a sequence of nested closed and bounded interval, or a nested sequence of closed and bounded intervals. So this is what the thing is. Now, so what does the theorem says? The theorem says if the lengths of these intervals A1, B1, and then the length of A1, B1 is, you see, the entire length of this line segment. A2, B2 is somewhat smaller than the length of A1, B1. The length of A3, B3 is sometimes smaller than A2, B2. The length of AN, BN, so that is decreasing and so on. So the lengths are actually decreasing, and if this entire thing goes to 0, all the lengths, so AN is coming from this side, BNs are coming from this side. So if they do not want to leave anything in between them, they want to squeeze into one another, ANs and BNs, then we can guarantee that there is exactly one point in the middle of everything. That is our point, singleton set Z. There the intersection will be non-empty and there will be only one point and nothing else. There cannot be anything else. So now, before going to the proof, let's see how does this one help in our solving this problem with triple dots, dot dot dot, in the representation of root 2. So what happens, you see, we see square root of 2. So let me copy this one first. Yeah, copy. Okay, fine. So this one is in at the beginning 1 and 2. So the value of root 2 is in between 1 and 2. This is my A1 B1. A1 B1. Okay. Then what we get is root 2. Oh, this is better. Yeah. This is in a 1.4 comma 1.5. Okay, so this is there. Now again root 2 is in 1.41 comma 1.42 and so on. So yeah, so this is my A3 B3, and yeah, earlier this is my A2 B2. Okay, so A1 B1, you see, A1 B1 1 2 contains A2 B2. A2 B2 is just a subdivision of the entire interval 1 to 2, and root 2 falls in between that 1.4 to 1.5. Then root 2 again, if you subdivide a to b to 1.4 to 1.5 into 10 subintervals, then root 2 falls between 1.41 to 1.42, and then again root 2 falls in 1.414 to 1.415, and so this is your A4, B4, and so on. So now you see length of A1, B1, length of A1, B1. So B1 minus B1, why am I putting a modulus here? B1 minus A1 was 1. Then you had B2 minus A2 is equal to 0.1. Then B3 minus A3 is 0.01. Then B4 minus A4 is equal to 0.0001. How many? No, 2 zeros. 0.01, and so on. So this is going on. So at the last, what we will get, and not at the last, I mean in this way we will get that Bn minus An will be how much? 10 to the power. So for B1 minus A1, this is 10 to the power 0. B2 minus is 10 to the power minus 1. So 10 to the power minus n minus 1. Okay. So you see minus n minus 1. No, not this way. Here it will be minus, and here this. Yes, fine. So this is what is going to be. So then you see infimum of Bn minus An, the length of An Bn is going to 0, decreasing to 0. So then Cantor's this theorem, Cantor's nested interval theorem, will guarantee that you have got a particular number, a unique number over there. So that number is my root 2. So that cannot be anything else, since root 2 belongs to all of them, all these A and B n. So that number has to be root 2. So this way, Cantor's theorem actually guarantees the consistency of decimal representation system. So now let's see the proof. Okay. So we'll come back to some more discussions on this one again later. So now for the time being, let's see the proof. So what is the proof? Proof goes this way. Now from this line, I'll just copy this one over here. Proof, since this thing happens, what happened? Okay, I'll just put over here. What is your problem? Why are you not? Okay, I'll just do it this way then, a little bit. Yeah, since yeah, this is better. This is there. We can say we have this thing that A1 is smaller than or equal to A2, smaller than or equal to A3, smaller than or equal to, and it goes on this way. So dots, and this is smaller than or equal to An, and this is smaller than or equal to, goes on infinitely many between them, in smaller than or equal to Bn. This is smaller than or equal to, this goes on again. Then over here, this is B3 less than or equal to B2 less than or equal to B2 less than or equal to B1. So this happens. Okay. Okay. So this inequality is you get from this nestedness of the intervals, subintervals. Okay, so now what happens? So this is it. So now we consider two sets. So consider two sets. Number one, A, which is the set of all left extremities, left endpoints. So set of all ANs, N is in coming from N. So this is set of all left endpoints, and consider A set of all left endpoints, and B as the set of all right endpoints. Okay, so this is set of all right endpoints. So this is my A and this is my B. Now clearly A is non-empty, of course, and is bounded above See here, this is my A1, here you have got A1, here you have got A2, here you have got A3, here you have got AN. So all these things are there. All the ANs are supposedly, we guess that, we supposedly to be right of this this point of interest. Okay, this is the desired point, xi. So all these points are supposed to be to the left of this xi. So A, the set of all left endpoints, is bounded above set, and this is bounded above by any of these B's over here. So I'll choose, say, B1. So clearly A is non-empty and bounded above by B1. Let's say B1. Okay. Then by completeness property, supremum of A exists. So call this supremum of A, as the point xi. We suspect that the supremum of all the left end points would be this xi. Similarly, we could have done the same thing using the BNs. Now, the set of all the right endpoints B, this is bounded below, and hence infimum would exist. Infimum for B would exist, and choose the infimum of all the B's as your xi, and that would serve as well in this proof. Okay, so by the completeness property, supremum of A exists, called supremum of A is equals to xi. Now we will show that the xi is the infimum of all the Bn's, or let's say xi is a lower bound of all the Bn's out there from B, from the this set B. So let's see. So we claim that. So we claim that for all n, this xi is smaller than or equal to the Bn's, because this is a, and this works as a lower bound of the set B, this set B. Okay. So how do we prove this? To prove the claim, assume the contrary. So assume that there exists a BK, let's say BK from B, from as a BK, a right end point, such that BK is smaller than xi. Okay. So what contradiction does it make? Then what we have, since xi is equal to the supremum of A, and bk is something smaller than the supremum, and bk is something smaller than the supremum, by the property, by the definition of supremum, we will find a number which goes between bk and supremum of A. We find a element from A which goes between bk and supremum of A. That is the definition of supremum. So we find there exists some AP, let's say, from A, such that AP lies between this thing BK, strictly smaller than AP and less than or equal to xi. Okay. So what we have assumed that here, somewhere here we have got BK. Okay, somewhere here we have got BK, and since here we have got BK, we have AP over here. So here you have assumed, here you have BK, and here somewhere here you have got AP. Then you choose, so this AP will correspond to some BP as well. So let's see that. So choose this thing. The maximum, choose max m is equal to the maximum of K and P. Then what happens? Then we get m is greater than or equal to K, and also m is greater than or equal to P. So therefore we have AM will be greater than or equal to, let me write it this way, then P will be smaller than or equal to AM, and BM will be smaller than or equal to BK, right? This comes from the definition of this nestedness of this collection, like A1 less than or equal to A2 less than or equal to A3, this one. Okay, so this is there because say your key is 100. So let me write over here, key is 100. K is say 100, so B100 falls over there. So B, let's say 100 is smaller than xi. Okay, B100 is smaller than xi. So in between B100 and xi, there must be something like something from A. So A, let's say 90 is over there. So A90 falls between B100 is strictly smaller than A90, and this is less than or equal to xi. Okay, so this happens. So therefore now where will so then M is your maximum of 90 and 100. So that is M is 100. So then what happens? A100 by using this property, A100 will be bigger than or equal to A90, and okay, if this is not something very, then A100 is I'm writing what I've written. A90 will be smaller than A100, and And what about B100 and yeah, B100 is there. B100 is there. So B100 is there. So that is the maximum of 100 and 100. So B100 is there. So then what happens? Since A100 and B100 is an element in this sequence of A and Bn, what we get is A90. What we get here is A90. A90 is smaller than or equal to A100. This is obviously smaller than B100. Okay, this I mean, this is obviously true because this is coming from the hypothesis of this one, the nested interval. But what we have got here is B100. Over here you see B100 is smaller than A90. So here you see B100 is smaller than A90. So now this one is a contradiction thing. B100 is strictly smaller than B100. This is a contradiction. Same number B100 that is smaller than itself. So that is a contradiction. So let's come back here. Choose m equal to maximum of Kp. Then for m greater than or equal to P and m is greater than or equal to K and both P. Therefore Ap is smaller than Am and Bm is smaller than Bk. Therefore this one Bk less than Ap. Therefore Bk less than Ap. Let me do one thing. Okay, over here, yeah. Ap is smaller than equal to Am. This is smaller than or equal to, not equal to, smaller than Bm. This is smaller than Bk. So is a contradiction, since Bk over here has become smaller than itself. So that is a contradiction. So therefore, now I delete this thing. So therefore what happening? Therefore this assumption is not true, so our claim is proved. Okay, so therefore our claim is proved. That is for all n in N, xi is smaller than or equal to Bn. Okay, xi is smaller than or equal to Bn. Fine. So therefore, what we get here is, so hence we can write this way, that for all n what happens is this An is smaller than or equal to xi is smaller than or equal to Bn. So this happens for every n. That is implies xi belongs to An, Bn. This happens. So that means so xi is in each one of those subintervals A and B, and then xi is in the intersection of all of them. I'll just copy from here. Intersection of all of them. right? So we have first proved that this intersection is non-empty. Therefore, this intersection is not empty. Okay, done. So next thing we need to show is that the intersection contains precisely one point. Okay, to show this thing, to show this thing is the singleton set xi and nothing else, assume there is something else as well. Assume there is something else as well. So assume there is eta in there in the interval. So what happens? Therefore, what about the distance of xi and eta? This thing must happen that their distance is definitely positive, non-negative, let's say. Then xi minus eta, since that is there in all of them, understand this thing, that xi is in ANBN, xi is in ANBN for all of them, and eta is also in ANBN. So the if eta is somewhere over here, then the distance between xi and eta will be smaller than the length of ANBN for every n. The distance between xi and eta will be smaller than the length of every subinterval A and Bn. So the length of xi and eta should be smaller than or equal to Bn minus An for all n. This should happen for all n. This must happen. Therefore, this xi minus eta, the distance xi minus eta is, okay, I cannot take the limit yet. So therefore, we'll use the property that infimum of Bn minus An is 0. So since, I'll remove this, therefore, since the infimum of Bn minus An is equal to 0 for every epsilon greater than 0. I'll copy this epsilon here. For every epsilon 0, we find AMBM. We find this AM already used. Okay, so what is not used? Say Q. AQ, BQ, such that AQ, BQ, such that this thing happens, that 0 less than BQ minus AQ is smaller than epsilon. This must happen by the definition of infimum. By definition of infimum is 0. So therefore, and they are obviously non-negative. So therefore, if epsilon is anything greater than 0, greater than the infimum, so there will be something smaller than that. Some element from the set which is smaller than anything greater thing. So this means that the length from here, that since this is smaller than Bn minus An for every n, so therefore this we get zeros less than or equal to xi minus eta. This one is less than or equal to bq minus aq as well, so bq minus aq as well, and this is smaller than epsilon. So what is happening? Xi minus epsilon, the xi minus eta, the distance is smaller than any positive number epsilon. So therefore xi minus epsilon has to be 0. Xi minus eta has to be 0. There is no other way out, because xi minus eta is smaller than every positive number epsilon. So xi minus eta has to be 0. Therefore xi is equals to eta. So this shows that there cannot be more than one point in the intersection of all of them. So this completes the proof. Okay, this completes the proof. Fine. So yeah, the proof is done. So then we are so now once this proof is done, so how does this one address the equation of two different representations like the one we saw, 1 and 0.9 over here, 0.9 recurring and this one. So this is our next question to answer. How does this solve the make the how does this justify the consistency of different decimal representations of the same number? So let's answer this one now. Suppose we have got we want to measure the length of a rod which we know to be half, 0.5 or half. We should not say 0.5, say half, using this method. So we start with this way. So let L be the length of our rod, which is half we know. Fine. So now let us apply this theorem. So firstly, what we'll choose, L will be in A1, B1. Sorry, I have chosen this one first. L belongs to 0, 1 first. Call this A1, B1. So we do not have any problem in that. No. Next, then we subdivide this one into 10 subintervals, 0.1 to 0 to 0.1, 0.1 to 0.2, 0.2 to 0.3, 0.3 to 0.4, and so on, 0.9 to 0.9 to 1. So then we see that L falls in two different subintervals, 0.4 to 0.5. So okay, so divide 0, 1 into 10 subintervals. Then L falls in both 0.4 to 0.5 and 0.5 to 0.6. So which one do we choose? choose? The answer is anyone. Anyone we choose. So suppose we choose the first one. Let's say 0.04 to 0.5. Okay, 0.4 to 0.5. Then in the next step we subdivide 0.4 to 0.5 into again 10 subintervals, 0.4 to 0.41, 0.41 to 0.42, 0.42 to 0.43, and so on, 0.49 to 0.5. So then L will again, then in the, I'll write, then in the next lot of subdivisions, there is some problem, spelling mistake. There is in the next lot of subdivisions, L falls in 0.49 to 0.50. Okay, do you see now? In the next lot, of subdivision, L falls in 0.4999 to 0.500, right? So now you see where we are going. So and so on. So now if you keep on doing like this, Cantor's intersection theorem. So if we keep on doing like this, the theorem, that is Cantor's nested interval theorem, guarantees that there is exactly one real number in all of them. Hence we choose any representation of A. So this is how Cantor's intersection theorem solves the consistency of decimal representations. So that's all for today. Thank you so much. I'll be sharing this PDF of this one alongside the video.